Hello, everybody. I see everybody starting to fill up the room. Thank you very much for joining. I'll wait a couple more minutes here while everybody joins. I see a few people I recognize. Hey, Sam. Nice to see you, Christoph. I see Juan's on the line also. Okay, thank you, Jerome. I see that we're ready to get going then. So I'm going to go ahead and get started. Move this out of the way so I can see my slides, and we can get rocking and rolling here. Good morning from northeastern Pennsylvania. It is going to be an interesting day. We're expecting somewhere around 18 inches of snow today, so it's going to be an interesting event. It's going to happen. We may actually set a record for the most snow in a 24-hour period. With that to look forward to, this should be a lot more fun. Because what I'm going to talk to you today about is managing the complexity of innovation. My background, I've been doing this for quite a while, and I've started my introduction to innovation. It's pretty long. I basically started understanding systems with a family-owned dairy farm that my father had, and learned a lot about how the complexity of things exist and how they kind of work with basically planting seeds and growing product. That eventually led to me, but the farm was too small for me, and I wanted to do something more exciting. And I always loved electronics, so I moved into that space. So I developed engine controls and flight controls for the U.S. and the DoD to DoD and FAA standards, and became an electrical and software engineer, doing that for about 10 years of my career. From that, I moved into a consultant for automotive, medical, and industrial products. I did that for quite a while, and my goal was basically reducing the time to market. I did that for about 10 years and really gained an appreciation for how system engineering could help reduce the product development cycle. From there, I joined Siemens after learning about a product, and I joined Siemens, and now I support Siemens products. I've done everything. I've done everything from deploying them to customers to developing them, and now I'm basically working in the area of defining solutions around the systems engineering space. But still, that's not quite enough. I enjoy mentoring and coaching, and some of the topics that we're working today, I've actually coached 8th graders with, and really have enjoyed reaching out to the community and helping give back. My topic today is about innovation, which, innovation is a very simple concept. It's about bringing an idea to life. It's basically bringing it to a product. It can be something that's very simple, but in reality, today, nothing's really simple. Everything is connected. Everything is rich. Everything requires basically multiple pieces that have to be put together and to build a system. There's no simple system anymore. Everything's connected. Many times, some things are systems of systems. So today, I'm going to basically talk about 3 things that I feel that you need when you move to these complex systems. You need to be able to capture everything from the problem to the solution. You need to be able to show how everything is connected together to do that. Next, You need to be able to engage others. You need to bring other into your organization that can help build the product. You need to be able to work with suppliers. You need to be able to work with partners to basically do that. And finally, you basically need to leverage knowledge. You need to be able to take the information that you've built over time and basically bring that information into current products. You basically need to assemble things together. And those are things that you need to basically build these complex systems of today. Now, what I'm going to do for this, I'm going to walk through kind of an example to kind of show you what I'm talking about with this. I'm going to use a medical device example for that. And the history of this medical device example actually came from an FDA request that came to Siemens that said, can you show us some of the latest technology that you have to help develop these systems and around your digital information, so that you can basically use digital techniques that are current and basically bring that into your product. So with that request, I got involved because I was asked to, can you support the system engineering, mainly the system modeling aspect of it. And I developed a model of the ventilator that was an open source design, and you can actually go and get this information, and I'd be happy to provide it to anybody, the model that we built. But basically this model was a ventilator, and we looked at everything from the problem, starting with what the problem was that they were working with, all the way down to the solution, down to basically defining the functions of the circuit boards of the system and the software of the system. And then when we finally got that done, I was like, wow, it'd be really great to be able to get some feedback on this, and maybe we can even use it to get a more innovative idea of what could help solve today's problems. With COVID-19 raging at the time, and back in April, I decided, let's go talk to someone. So I actually went to the local hospital here in town and talked to Jeff Franco, respiratory therapist there at the hospital. And it was interesting that the very first thing he said to me, he said, you got the problem wrong. And I go, I got the problem wrong? He said, yes. Said, we need to reduce the PPE. And, basically with a ventilator that you're showing me here, it doesn't really help. What we really need is some way that we could actually go in and, we could actually remotely control this ventilator. He said, every time I have to go into the room to basically make an adjustment, I have to gown up and put all my equipment on. And in a small hospital like we have here in our town, PPE is expensive. We could say, it's on the orders of every time they gown up, it's tens to $20 to $100 of material that they have to put on. And I had some statistics of how much it could save just in one day if you didn't have to go into the hospital to basically do this, and into the room to do that. So that's my example of basically capturing the problem and solution. You need to be able to show how you went from that idea, and that's what we did with this ventilator. Is we actually looked at the problem and said, hey, what would it take to do remote operation? And then as you go through the remote operation, you look at that from an operational analysis, what would be needed. Then you start looking at from a system analysis, what would that take? You basically want remote control of some site, and then you want to be able to do remote operation all the way down, and you want to be able to do that all the way down to your components. So in doing this, we actually are leveraging the technology of the functional chain that's part of the Capella tool set. And this connection all the way from capability down to the components helps reduce that complexity of the system. By knowing how everything is connected together and basically being able to communicate that and follow that, it helps in all different ways. And I'll kind of show you how that works here as I walk through this example. So the first thing we did is we realized that from the operational analysis, we needed this remote control operational capability that needed to be implemented. And then in that operational capability had to lead to some activities. As you can see here, one of the activities is to adjust the remote. So basically I want to be able to do that as seen here in the green flow. From adjusting the remote, you want to basically figure out, well, what's going on inside the system. So we need to basically interact via the remote operation and remote monitoring. We need to go directly inside of the ventilator system and affect things like the provide respiration data and to actuate the operating mode. So you basically want to be able to change modes from outside the system. You want the therapist that's basically outside the room, basically interacting with the patient room, with the ventilator that's in the patient room. And that then leads to more of a logical design of what that functionality has to be. You want to be able to do the remote operation that's basically happening through some type of remote UI device that's basically outside the room, but still now part of this ventilator system. So you want to be able to have this connection between it. So you want to have that flow of this remote operation. And that then starts leading into developing the hardware design of the system that could do that. And one of the things that Jeff even recommended, could you hook up an iPad? It'd be really great if I had an iPad that I could do this with. Because with the iPad, I'd have the ability to have an application on that iPad that could authenticate and configure and monitor the data. And it could be connected right through the hospital Wi-Fi system that we could do that. And lo and behold, it actually isn't that, there's already hooks there. We had a USB port that we could leverage to basically allow this connection from this via a Wi-Fi hub, a Wi-Fi fob to a hub to the internet. We could actually have this connection of functionality passing from the iPad all the way over to the remote Wi-Fi. So all the pieces were there, and that's the power of basically using a rich methodology on top of a language to help communicate this. We were also able to bring in the requirements and get the requirements capturing of what the connection was going to be. And then we could map that requirements right back to these functional flows that are going through the system and connect them together so that we now have a connection all the way from the requirements, all the way from the operational analysis, essentially down to the components. So that's one of the powers that you really need. One of the three things that you really need to manage complexity is being able to show how you can go from capability essentially all the way down to the components that are basically going to deliver that capability. Now, next on this is engaging others. Now, building a system like this that we were just talking about, adding that new app, that's a little bit outside the space of a typical company that's working on building ventilators. They may not be the expert in essentially that field. So they need to basically engage others. Innovation is interesting. The innovation matrix is kind of key to this kind of figuring out where you are. And as a ventilator manufacturer, I may be expert at sustaining innovation. I know exactly the problem. I know exactly the domain. But when you start moving into these new technologies to build an app in a cloud, you're not in my comfort space. So basically, I'm over here in this kind of unknown domain, and I'm kind of working. So yeah, maybe I'll come out with a nice little breakthrough, but I'm not going to be able to do that over and over. So what you do is you start looking for companies that I can work with and engage with to help deliver this new app and this new technology to it. And so what you need to do is you need to be able to take that model that you've worked on before, and you want to be able to pull a subset of that model out. You want to identify that for the supplier so you can go off and develop it. So you need a way that I can leverage this knowledge that I have in these models and basically bring it out and share it with suppliers. And one of the ways that you can do that is basically you can use this, you can take part of the model and basically do that. Now, the reason why it's important to have this way of carving part of a model and be able to give it to people is that you don't want to basically give them the whole model, because your intellectual property is in the first model. So you want to basically carve out a piece of it and be able to take that model and then create a model that's specific just for the needs of the customer or the partner you're going to work with. In this case, I've ripped out parts of the model that represent the cloud and the iPad and the therapist, and basically just a subset of the ventilator model here with the Wi-Fi components in it. Once you have that information, you want to basically control it. You want to make sure you have some way of controlling this into some type of system of record. And an example is our Teamcenter product, which basically we can then save these models into Teamcenter. And then with Teamcenter, we provide basically a secure environment that you can basically give a portal to your suppliers so that they can get in and use it. So this is important, that you have a way to exchange this information with the partners in a reliable and secure fashion. Once your supplier gets the information, they need to be able to interact with it. They need to be able to give comments, basically add status to it, maybe update ideas with you and exchange ideas with you, again, through a secure portal of some fashion. And then last of all, they need to be able to go in and actually add their own content to it. So they need to be able to launch into the modeling tools such as Capella and basically start making editing changes to it. In this case, we're showing our Siemens product that's based on Capella, System Modeling Workbench. Once they bring that into the model, they can go work on it, they can check it in, check it out, add their content to it, and then essentially save that information back and publish it for review by the supplier. So those are two of the things that you need. Basically, you want to be able to engage others once you have this problem and solution captured. Now, on the very last item here, seems like it should be fairly simple, you would think. The last item is leveraging knowledge. And leveraging knowledge is really about, I want to build upon what I've built before. Now, this seems odd that I have to actually say that this is important, that you want to build from components, but system modeling methods have struggled essentially over the years to really do this, to be able to build things out of components. It's strange in a way, because you think of a CAD system, would you ever consider that to build this ventilator that, or to build even build this ventilator, that I would have to build the entire 3D model of it all in one file, that I couldn't have some components that I could build it up from, that I couldn't have the compressor, or I couldn't have some sensors, or I couldn't have the hoses even represented as different 3D files. They all could be leveraged together and used at once. But interesting enough, system modeling has lagged behind this, and building up from components is not something that typically has been available. 1 second. So this is kind of the final thing that we need to be able to do, is that we need to be able to build components and libraries of components that we can then lead to sustaining innovation based on the fact that we have these components that are out there. So in the example of the ventilator, we want to be able to have a remote wireless interface component, or a sensor component, or microturbines, or solenoids, or vent circuits. These are all things that could basically be components that I could build a bigger ventilator system out of. As you mature, this would be typical. But it is surprising that it's been many years that system modeling has been out there with SysML, that this support really isn't common. So an example of then how this could be done is that you want to be able to essentially log into your system that has your models and components in it, and you want to be able to locate, let's say, the ventilator that you have. And once you locate that ventilator, you just want to be able to bring that information into your system for you. You don't want to have to be searching and looking and finding that information. You want to be able to view the model that you've saved away, and then basically open that model and bring it into your modeling tool. And when you bring that model into the modeling tool, you don't want to be thinking about, oh, I need this configuration and this version and this variant portion of it, or this effectivity. You want that information to be part of the model that you saved, and you want it to be loaded automatically for you and then ready for you to start working. And that helps you manage that complexity of these very complex systems that you're going to be building up. So you basically load the information in. Once you have the information in, you've got the models loaded, and you can start working on that very, very quickly and very easily. So basically summarizing now, I'm basically going to back and review. You need the three capabilities. You need to be able to start with the problem in the solution. You need to be able to start with basically looking at what is the raw capability that I need. In this case, the remote operation was the capability that I needed. I wanted to be able to bring that remote operation and turn that into a capability for the system that basically was to basically give that capability. Then I started capturing that capability as a flow of functions to deliver this remote operation. Once I had that flow of function, I was able to basically then take that flow of functions and connect them together through various components that basically that implement that flow of that remote operational capability. And then finally, I was able to realize those components in actual physical devices, such as iPads and the clouds and the CPU board, to basically deliver that whole functionality. The next thing, again, that you need to be able to engage others. You just can't do it alone with these complex systems, even as something as simple as a ventilator. And just imagine what it would be like to nowadays to build a vehicle or to build a transportation system. Everything is changing. The architectures of products are changing dramatically. We're going from internal combustions to fuel cell based systems. The whole design is changing in different ways, and with that you need to engage others to help you deliver these new, more complex systems. And then finally, you want to be able to leverage your knowledge. You don't want to basically stay in the past and keep using things the same way or building one model. You want to basically start building things together and putting together products that are much more complex than what you may have been able to deliver before, by basically leveraging the technology that you have, and even more importantly, leveraging the technology of your suppliers and your partners that may be bringing into the fold. So anyway, that kind of concludes my presentation. If you want more information on the ventilator example that we put together, my associate Larry Sampson has a YouTube channel that has out Lunch with Larry. It talks a lot about how we took this ventilator model and we basically tied it into all different products, upstream and downstream, kind of looking at the whole big picture. So we have that out there. I also did a Capella Day presentation where we jumped into a little bit more detail on the details of the model and talked about how the model basically was represented and developed. And then, and that's all I really have today. I'll take some questions if you have them. But thank you very much. We've got lots of materials that I could help share with people. You can please look me up on LinkedIn. Thank you. Yeah, I have one question here, but people are asking what my experience was with sharing Capella models with non-engineers. And the truth is, yes, it's very easy to share them with non-engineers. My first experience really working with non-engineers was with a team that I was working with, and it was a 4-H team. I don't know if you're familiar with 4-H. It's an organization here in the States that does agricultural activities with children, young people. And I got in, I basically got involved with a small team that was developing a product, and their product was pretty complex. And I said, do you need some help? And of course they said, yes, we need help, please come help. Especially the teachers were like, please help us. We can't understand what these students are telling us. So we actually used Capella with these 12 to 13-year-old students. And actually I think some of them were as young as 10. And we captured their model, which was essentially like a device that would send a notification if somebody was hurt and they were out in the field. But they were using low-rad communications, basically a low-power communications network instead of using Wi-Fi and cellular. And so that system was pretty complex. It included a fob and a base station, all that. And one of the guys kind of had it in their head, but he wasn't able to communicate it very well to anyone. And it was only after about 2 or 3 sessions of using Capella with them that we were able to have the teachers understand finally what they were talking about. We went all the way to logical modeling and picked out various components and linked them to Amazon, and they were able to order the parts. And eventually they went on to win their state competition here in Pennsylvania. They got a $4,000, nice little $4,000, $1,000 each per scholarship for going to school. From the local area, from the statewide organization for it, and they got a nice plaque and certificate. Unfortunately, COVID prevented them from doing that session this year. I was looking forward to taking it right down to a product. So, from which layers of Capella are you performing the EBOM or logical or physical? From Capella, we're basically going down to the physical level with it. We aren't. A lot of times I don't get into the end product breakdown structure because then we start working with our PLM tools to do that. The PLM tool is what captures the EBOM or electronic bomb. The idea is to use the physical decomposition and then essentially link to that EBOM level that lives in the bill of material that would have it. I mean, the idea is to kind of figure out what you need with the physical architecture, and then map that to what might actually be called a configured component. That's at the next level. Questions? So as far as the different flow of the different streams, you're thinking of the architecture is really kind of like the blueprint that you're developing. And so it feeds those streams. And in many ways, it acts to coordinate from them. The electrical domain, the fluid domain, they all have different languages of their own. They all have different tools. And in some ways, they may actually have their own architecture. So for instance, you may not want to get down to the level of detailed of capturing in your Capella model a PI and D that you may have for doing piping and instrumentation, for instance. So basically you would kind of stop at the Capella level and not go down to the level of detail that you might actually have in that type of hydraulic or flow model. But the problem that the power that you have is now you have a common language with Capella that you could at least communicate, well, what does the control system maybe need to do or have to do that would map to that PI and D. So it's always a little interesting trying to figure out, well, how far do you need to go? The key is you go as far as you need to go with the Capella tool, that I can define what the downstream environment needs, or downstream tools need to do their job. So for instance, with a circuit board, I may be down to the level of defining that I need this functionality from the circuit board. I need a level of functionality of, let's say, PWM control. So I'd have that function maybe captured in my circuit board that's allocated to it as a function. I don't need to go down to start defining out what the parts are, the components are, because that can be better done in the ECAD and MCAD domain. But getting to that bill of function, so to speak, is something that I could then hand off to the circuit board designers to go and find out what they have that matches my needs and be able to go find. And that's essentially what we did with the small team that I was working with, the students I was working with, is they figured out what they needed. They needed some circuitry to be able to do low power communications. And then we went off searching for, well, what technology is available for doing that, and what we could pull off the shelf became the solution for that. Okay, let me see, anything else? Simulation would be extremely helpful. Stay tuned, there'll be more. There actually are some products that are starting to do simulations with Capella that are out there. Siemens is working on that. We've actually had success tying some of our Capella models to models in MATLAB models. So it's an area that's the ecosystem around Capella is growing rapidly, and we're actually very happy to be part of that ecosystem. So there's nothing. We're not done yet. We're just starting the road to build out that ecosystem. Okay, I'm going to go ahead and stop the recording.